Hi everyone, I'm Aouad, and I'm thrilled to present our research on online assortment optimization for two-sided matching platforms. And this is a joint work with my colleague Daniela Saban from Stanford GSB. What motivates our work is the growth of matching platforms for online labor markets. I'm giving here a number of well-known examples of platforms that operate in different sectors. When many of these platforms have in common is a relatively similar matching process in which one side of the market initiates the matching. So for example, on Design Crowd, which is a design contest platform, the designer will search and browse through an assortment of different contests that are currently open. For example, this could be firms looking for a new logo to be designed. And then out of this assortment, based on the designer's preferences and skills, he or she will choose which contest to apply to, which firms to contact. And then finally, they will learn the outcomes of their submissions once the other side of the market, once the firms reviews all the submissions and decides which ones to reward. So what does the platform control in this process? Well, it can really influence the outcomes by carefully designing the initial assortment of a contest that is displayed to the designer. So both controlling the variety of contests that are shown to a particular designer, but also maybe the way these contests are displayed and ranked on a web page. And this is, from a decision-making perspective, this is essentially analogous to the issue of assortment optimization, which has received a great deal of attention in the operations literature. However, this literature focuses mostly on retailing applications. And this is where the analogy breaks. In retail, we're dealing with one-sided preferences, whereas in matching, there are two-sided preferences. So let me explain. In retail, each customer has preferences over the products that are offered to him or her, and out of which it chooses which product to buy, and then the transaction occurs. By contrast, in matching, not only the consumer side, say the designers in the example, have preferences over the contest, over the listings on the other side of the market. But once a matching request is made, once a submission is sent, there's also a review process on the other side of the market. The suppliers will, or the firms will have received a number of submissions, and then they will choose which ones to reward based on their own preferences. So we do have preferences on both sides of the market that influence the market outcomes. These preferences are combinatorial in nature, and as such, the question that we want to think about is how to incorporate two-sided preferences into assortment optimization modeling. So our first contribution in this regard is to develop a model that can push this analogy between assortment optimization and matching platforms that we call online two-sided assortment problem. The preliminary results I'll mention here in this talk are regarding the differences between the classical one-sided assortment problem and the two-sided setting. And this surfaces when we analyze a simple greedy algorithm. And we show that this simple greedy algorithm actually achieves the best possible competitive ratio in adversarial and stochastic settings. This is by contrast with one-sided assortment problems where the literature shows that it is possible to design algorithms better than greedy. So our main contribution, which is the third item on this slide, is to think of how do we go past this impossibility and develop algorithms that achieve higher competitive ratios. And our key finding is that what really shapes the structure of the problem is the choice model of the suppliers, which is on the receiving end of the market. Those are those who receive the requests and then review them. And we actually provide algorithms that can leverage any prior knowledge about the structure of the supplier's preferences to achieve higher competitive ratio. We call these algorithms preference-aware balancing algorithms, and we exemplify our framework using Logit-based choice models, multinomial Logit and nested Logit models. So let me describe the model first. So we have customers, platforms, and suppliers. Customers arrive one per period. Each of them is endowed with a choice model that describe preferences over suppliers, and these arrival process is exogenous. Similarly, for suppliers, there's an exogenous process that describes which of them are available at any point in time. And each of them is also endowed with a choice model that describes preferences over the consumers, over customer sets. So how does the dynamics works out in this model? There are horizon of T periods. At the beginning of each period, there's a new customer that arrives. The subset of available suppliers can be updated as well. Then the platform observes the supplier set and the consumer type and accordingly chooses an assortment to offer to the consumer. So these are the designers in the example we provided initially. And then out of this assortment, the consumers will express her preferences by choosing at most one supplier to match with and then send a matching request. And we'll focus on this setting in this talk whereby there's at most one choice made by the supplier. And then finally, suppliers at the time of a permanent departure will review all the requests they have received from customers over time and decide which ones to pick, whether to pick any of them, and this is based on their own choice model over customers. So highlighting here that the supply decision is delayed, okay, by nature, that the suppliers can stay in the market longer than customers, and as such, they will accumulate a subset of customer requests potentially from which they can choose. And then the match occurs if any of these customer requests are agreed on. The goal of the platform is to maximize the expected number of successful matches. And the key input is going to be for us to think about the supplier's choice model, WIC, which you can think of as a function that gives a probability, an aggregate probability that each supplier I accepts any of the requests that they have received, which is denoted by C. And we'll in general, assume that this function is monotone, has diminishing returns. So for example, in retail, this would just be a binary indicator of whether any customer at all has purchased a given product I. But in matching settings, this is where we would have combinatorial preferences. For example, they could be captured by the multinomial Logit model, which means that the supplier assigns an attractiveness to each of the customer requests she has received. So the objective function is then expressed as the expected total number of matches obtained by summing over all suppliers, the aggregate probability with respect to the final set of customer requests that is induced by a policy pi. So we'll compare the algorithms with designed to a clairvoyant benchmark, which knows in advance the sequence of customer arrivals and supplier sets, but doesn't know the random choices that occur throughout the process. And in terms of performance analytic metric, we'll use a standard notion of competitive ratio, which is the worst case ratio between the algorithm we develop and the clairvoyant benchmark. So let me start with a number of preliminary technical observations that help also position our model against the existing work on one-sided assortment optimization. So we'll focus on the greedy algorithm. This is an algorithm that picks an assortment A out of all the suppliers so as to maximize the immediate reward, the immediate increase in matches from the request of the current customer. And there's randomness here, obviously, due to the random variable xi of A, which depends on the random preferences of the current customer. So what we show is that the greedy algorithm achieves a competitive ratio of 1/2 under adversarial arrivals and 1 - 1 over E under IID stochastic arrivals. And this is based on extending known results for special cases of the model we consider. But the interesting part is that we observe at the same time that this 1/2 competitive ratio and 1 - 1 over E competitive ratio are essentially the best that can be achieved in the two-sided online assortment problem. And we cannot do better even in suitably defined asymptotic regimes, which are usually considered in the previous literature. And this is again creating a contrast between the problem we're studying, the two-sided problem, with the one-sided problem. So in the one-sided problem, the best achievable competitive ratio is of 1 - 1 over E, and it can be reached asymptotically. And this is what's shown by Golver-Zayatan in 2014. So in a sense, adding the consumer choices to the online matching problem doesn't make it harder from a competitive analysis perspective. And by contrast, our problem actually generalizes another class of online optimization problems known as online welfare maximization, studied by Kapralov et al. Among others. And as such, we inherit the 1/2 competitive ratio hardness that has been established by the literature. Okay, so we show the analogy between suppliers having rank-based preferences and the notion of coverage valuation functions that is appearing in the online welfare maximization formulation. So how do we go past this hardness, this strong hardness? Well, the key idea and our key contribution is really to think about how to incorporate the structure of the supplier's preferences and how to make the algorithms aware of this structure. And I'll start by summarizing first a framework that has been used extensively in the literature to gain tractability in online resource allocation problems. And there are two components, two ingredients. So first, we consider a scaling of the problem, a suitable asymptotic regime. Here it's governed by a parameter epsilon, and we call it a small probability regime. It assumes that any particular customer request has a small chance of being successful, at most epsilon. And this is a reasonable assumption for in contest design, where typically there's a very large number of entrants for any particular contest, out of which just one or up to three can be rewarded on this platform. And this generalizes the large inventory regime, small bid assumption in Aouad's problem. The second ingredient is an algorithm that improves on greedy. We call balancing algorithm, and it tries to strike a trade-off between the immediate rewards from the current customer and the potential future rewards from customers arriving in the future. And this is done through a discounting. So there's a discount function f, which is a crucial ingredient, and we discount according to the immediate reward according to the set of customer requests and choice probability of a supplier given the current request. Okay, so what we'll show and what we'll discuss next is how to calibrate this balancing function. And interestingly, while the literature has focused on exponential discounting functions for previously designed models, what we show is that we have to calibrate this balancing function based on the structure of supplier's preference. We have to make it preference aware. So what does it look like? Let's start with the multinomial logit as an example of our framework. So the multinomial logit assumes the following form on the choice probabilities of the suppliers. And this is our main result in this setting. So in a way that maybe is easier to parse, we show that if you can construct a balancing function that satisfies a certain ordinary differential inequality, then we can guarantee a certain competitive ratio. So the first part of this ODI, of this ordinary differential inequality, is about preference awareness. It captures the shape and the substitution patterns of the multinomial logit model. You can think of the two terms here intuitively as striking an optimal balance between immediate rewards and rewards from future customers. Then the second part of this ODI is actually the competitive, related to the competitive ratio that we can achieve. And our analysis is in the epsilon small probability regime. So the next question is, can we construct balancing functions that meet this criterion, this ODI? Can we solve this ODI? And we give an algorithm that can actually efficiently do that. And this is in red, the MNL-aware discount function that we compute. So there are two important observations. So first, good news is that in terms of competitive ratio, we can get kappa to be higher than 1 minus 1 over e. So we can break the 1 minus 1 over e barrier that is a fundamental barrier for other online assortment, one-sided assortment optimization problems. And the interesting bit as well is the shape of this function. So compared to the one-sided exponential function, we're really in a different realm. The discount function that we obtain numerically is concave rather than convex. And the way you can think about it is that in classical online matching and one-sided assortment setting, the objective function is additive. And in contrast, our setting has diminishing returns. So due to this diminishing returns, there's already a natural discounting happening. So we don't need to discount as much over time. And this explains that the shape of the balancing or the discount function is concave. Interestingly, and that will be our main technical result, we can significantly generalize and extend this result to nested logic choice models. So think of it as the fact that suppliers can partition the customer request into different nests that are of different types. And then there's a parameter gamma that can capture the degree of competition between the customers within the same nest. So, for example, experienced designers, unexperienced design, and gamma controls the degree of competition. We can extend our in result in this setting, and this is our main technical contribution in the paper. So it essentially changes, it's the same principle, but it changes the ODI. As you can see here, the ODI is more complicated, and the parameter gamma, and it depends on the parameter gamma of the nested logic preferences. So an interesting question I'd like to close the talk on is, what is the effect of gamma? What is the effect of competition? So on the plot in the left, I'm showing the competitive ratio we can guarantee by using different types of discount functions, whether it's an exponential discount function, the MNL-aware discount function, or a discount function that is calibrated to the ODI. And as you can see, there's a significant gap. So preference awareness matters. It can lead to higher competitive ratios that cannot be achieved if you're not calibrating your discount function to the preferences. The other interesting observation is that as gamma goes to 0, which is where we have more competition within a nest, then the competitive ratio goes to 1/2. And we can actually show that this is the best that can be achieved for deterministic algorithms. So the more competition, the harder the problem here is. And on the right plot, we're showing the different discount functions for different values of gamma. So you can see that they converge to the constant 1/2 function as gamma gets close to 0. So to sum up, what we've analyzed is basically differences between one-sided assortment settings that are suitable to retail and two-sided assortment settings which are suitable to matching. We show that under the key idea is that we can leverage structure of suppliers' preferences to achieve better competitive ratios potentially. The problem can be easier or harder than for retail. This strongly depends on the supplier's preferences. And we have a framework to develop and design preference-aware balancing algorithms that are calibrated to the shape of suppliers' choice model. Thank you all for your attention.